start our third session, and as before, we'll begin with our lecture on observing run preparations, and then we will do the hands-on module. So, delivering this lecture right now is Professor Robert Quimby. He is a PhD from University of Texas, followed by two excellent postdoctoral students at Caltech and at IPMU, Japan, Institute for Mathematics and Physics of the Universe. And he is now an associate professor at the San Diego State University. My main memory from his work is that he somehow seems to find supernovae that are order of magnitude brighter than what they should be. So I'm pretty sure that order of magnitude radiance is going to rub off in this lecture as well. So Robert, please.
All right, thank you. So I believe the kind of purpose of this session is to just prepare you for what you do when you have a telescope run coming up. So you've been lucky enough that you've been awarded time to use a valuable instrument to observe something in the heavens, and you want to make the most effective use of that time possible. So you really want to have a game plan going in so you know what you're going to do. You're going to have everything laid out, and then you're going to have a backup plan too, because things don't always go to plan. So I'm going to take a strong slant in this talk because I am myself a optical observer. I usually do observations in optical bands. All right, so we're going to start off just by laying out what you're trying to do here as an observer. And given my bias, so despite what we heard about the gravitational waves, I'm going to say your objective is to collect photons, right? Gravitational wave, they're great too, but for me, we're going to be collecting photons. That's our goal. You want to maximize that. That's your metric. How many photons you collect on some level is going to say how successful your observing run was. So you may have a set of targets, some number of targets. You want to get as many photons from all those targets as possible. Or you might have a large number of targets, and you just want to say, I want to get as many of these out as possible, so I need to observe as efficiently as possible so I can increase my number of targets. All right, so to kind of further my bias, I'm also going to assume that we are, so I should say this first. So, if you want to do that, if you want to get the most photons possible for all your targets, really what you want to do is make sure that the shutter on your telescope is open. You want to be collecting light the whole time. So that means you want to minimize the downtime. So it might, you take an exposure, you open up your shutter, you collect photons for maybe 5 minutes, and you close the shutter. And then you got to read out. You might want to change filters. You might want to move the telescope. So you should be thinking, can I do all those things at one time? Or do I need to do them sequentially? If you can do them all at once, great, you'll save a little time. And you also want to make sure that you're not at the telescope trying to figure out what to do. That's where this plan comes in place. So you don't want to be wasting time while you could be getting photons sitting there with the shutter closed talking about what to do next. All right. All right, so as I was saying, I'm going to continue my bias here. I'm not just an observer, but I'm going to assume that you're making preparations for observations that are going to take place on the Earth. All right. That has some consequences, so it's important that we're clear about this. You could be taking observations in space, and you have some set of criteria that you have to worry about when you're coming up with your observing plan for that. There's a different set of criteria that you have to work through when you're observing on the ground. One of the main things you have to cope with is the fact that there is a ground, right? And that means if your target is there, right, you're not going to see it. That's a big problem. So I know you guys, you've all taken probably at least a few years of astronomy courses, and you know the basic coordinate systems out there. You know we love coordinate systems in astronomy, right? Do you love the coordinate systems? Do you like them? All right. So you're probably familiar with this concept of a celestial sphere, and you can put different coordinates on that celestial sphere. You can have right ascension and declination, for example. For an observer on the ground, a handy system to keep in your head while you're at the telescope is the hour angle and declination system. Right. So I'm going to just kind of show you a few of the key points of that system just to remind you of how this works. So first thing we have to keep in mind is that we're on this round planet and it's spinning around. Right. So we can't see below us. We can only see above us, and because it's spinning around, we have a different view constantly with time, of course. Apparently what happens is the stars move across the sky. That's our self-centered way of thinking about what's really happening, was that we're spinning around and the stars are just sitting there. So there is some consideration you have to make for where on the Earth you are, right? If you're on the North Pole, everything's spinning around and the stars are just kind of going around like this. But if you're anywhere else, except for the South Pole, of course, you're getting different stars that are coming, rising, and setting, right? So you have to make sure, if you have telescope time on a telescope, you might want to check where in the world that telescope is located. Because if it's in the southern hemisphere or the northern hemisphere, you got to have a different visibility for targets. Okay, so for this coordinate system, where's north, by the way? I just got off a plane like a couple hours ago, so I don't know where anything is. Which direction is north? Can somebody point to north? I'm not the only one, huh? Let's say this is north, just for fun, right? That's due north, right here. That's due north. Okay, so here's how your coordinate system is oriented. Since the Earth is spinning around on an axis that goes north-south, we'll call this north, there's south, so that's going to be the east, where things rise, and that's going to be the west, where things set. Okay? You like that? If that's north, oh, I'm sorry, you're right. I'm sorry, I already have it backwards. So if that's north, then they're rising this way and setting. Thank you for pointing that out. Okay, so we have things rising. There is an imaginary line that runs right over our heads and connects this north point here and the southern point on the horizon. You guys know what that line is called? The meridian. Yeah, it's right there on the line there, so if that wasn't obvious. Yeah, that's the meridian. That's a very important thing, because what that is, that's the high point for whatever your target is. When that target is rising, it's going to reach its highest point when it hits the meridian, and then it's going to set after that. Right? So it's good to know where that line is and keep that in mind. And so as an observer, you can do everything kind of reference to that line. That's the most important line in the sky. And that's going to tell you how much time you have to observe your target before it starts setting. All right. So we, of course, have this one coordinate, which is your declination. So this is how far you are above the equatorial plane, right? So the equatorial plane is just a projection. It's just the Earth's equator. They take that Earth's equator and bring it out. So, all right. So let's say this is North Pole here, South Pole here, an equator like that. The equator should be in the middle, but that's close enough, right? So we have some rotation. Earth is spinning like that. So this plane here, your equatorial plane, you can project that out in the sky. Now, if you happen to be observing here at the North Pole, this is a very convenient place to observe, by the way. Well, for the math, it's convenient. For every other reason, it's a terrible place to observe. But if you're standing up here, of course, the plane of the ground happens to lie with the plane of the equatorial plane. They're coplanar, right? So here's your plane of the ground, and you're observing here, these nice and planar. We're not at the North Pole. We're over here somewhere. Close enough, yeah. So our ground plane is like this, and that means there's a very noticeable angle between the equatorial plane and the plane of the ground. So a declination of 0 where that equatorial plane is something like this. Okay? Something like that. So we call that declination 0, and then as you move up like this, all the way to the North Pole, that's 90 degrees positive and 90 degrees negative. Right? You guys know this system, right? Of course. The hour angle system is going to be based on the meridian line. Okay, so this is we got the north-south coordinate and declination. We need our east-west coordinate. This is going to be our hour angle. So the way this is defined is this is not a typo. There's a negative there. So moving from the meridian going towards the east is a negative change in hour angle. So if you go over this way, you're going to smaller numbers, more negative numbers. If you go towards the west, you're going to more positive numbers. Of course, there's 24 hours going around. They're not exactly the same, as you probably know, as hours on your clock. They're very, very close, but not exactly the same. Of course, because there's a difference between a mean solar day and a sidereal day. But for purposes today, I'm going to kind of blend those two together because it's 4 minutes a day. It's, who cares? Come on. I just lost like 17 hours, so 4 minutes, that's not a big deal. Okay, so it's just the number of hours over is going to be your hour angle. All right. All right. So of course, there's a relationship between hour angles and the right ascension coordinates that we usually assign to celestial coordinates. Hour angle is going to be specific to your location on the Earth, right? If you think about people here in India or people in the United States or in Japan, you're going to have a different idea of what the hour angle is for a given celestial object. So if we're all looking at some quasar off in the distance, maybe that's right over our heads in India, but that's not observable at the same time if you're in the United States. So the hour angle is going to be quite different. And of course, the relationship between hour angle and where you are on the Earth is dictated by what your longitude is. All right. All right, so the relationship between these two is thus. The hour angle is just the local sidereal time minus the right ascension. So what is the local sidereal time? That is the right ascension of an object that is on your meridian, right? So as time goes by, you got targets rising in the east, and you get up to your meridian, so the right ascensions are increasing, your local sidereal time is increasing, and you can compute what the hour angle is over in terms of just using this equation here. Okay, and rising targets have negative RAs by this definition. We could have defined it differently, but that's the one we're going to work with. Okay, so putting this all together in a little bit more practical sense. So if you want to compute what your local sidereal time is, you have to know something about where you are on the world, and you have to know what time it is in England, because that's where Greenwich, exactly. That's where they have it referenced to. So I picked a location on Earth. This is not where we are right now. This is where the Mount Laguna Observatory is. I happen to be the director of the Mount Laguna Observatory, so that's why I chose this. So you need to know what your longitude is if you want to be calculating hour angles from right ascensions. Latitude and height also help for other calculations, so I put that all in here. And then you can say, what is the time right now? And there's a handy function. This is an astroply time object here called sidereal time. And you can ask for what the parent is, and it'll do corrections for, what is it correct for? It corrects for, like, not precession, but it does, it's corrected for aberration, I believe. Yeah, well, I'll check that out. Okay, so you can run this through and I'll tell you what the local sidereal time is. So I specified, so I could do time right now. So this happens to be the local sidereal time in San Diego, if you're at the observatory there. If we were here, we'd have a very different local sidereal time because it's local, of course. I can also calculate, I guess I could, but I didn't run these other cells. So. Oh, put a $ instead of a thing. There it is. Okay. So that's the local sidereal time at some other time that I specified there. Okay, so as I'll show you in a minute, what we have ultimately here is we have a way to say how much longer do we have to observe that target. And you can see how this fits in with declination in a little bit. All right. Those are the constraints that come from the fact that we are on our curved Earth and we're rotating. If you're observing from the ground, there's one other important constraint that you have to take into account, and that is the fact that we have air above us. We have an atmosphere. It's great for breathing and living and all that, but it's not great for astronomy. It kind of gets in the way. So this is a quantity that you want to minimize if you're trying to do efficient observing. You want to have the least amount of stuff between you and the star that you're trying to look at. All right. So there's a concept of air mass, which is some measure of the relative amount of air between you and your target. And of course, this depends on what that angle is relative to straight overhead. If you look straight overhead, you're looking right through as little of the atmosphere as you can. As you start looking closer and closer to the horizon, you're going to get more and more air. How much more? Well, there's a pretty simple way to approximate this. You can do the plane parallel approximation. Pretend we live on a flat Earth, as many people in the United States do these days. And you can then calculate what this path length is relative to this path length doing simple trigonometry. So if you just look at the math here and you have this angle here, this is your zenith angle, the angle from straight overhead, the zenith point. The ratio between these two lines here is going to be given by the cosine of that angle there. So we can calculate what that air mass is, that quantity x is, for any zenith angle in our plane parallel atmosphere, and it's just the cosine of z is 1 over x, so we can solve that and we can calculate that. If you actually want to get something that's a little closer to reality, there's an equation you want to use. Instead of using a zenith angle, I've switched to altitude, which is just 90 degrees off from the zenith angle, of course. This is, again, approximation because really your air mass depends on what the air is made of, and is there clouds, and what's the temperature. So there's a lot of considerations, but this will get you pretty darn close. And we don't really ever care what that detail is for most of observing, because we, again, are trying to minimize how much air we're looking through. So we're looking overhead where these approximations are pretty good. So here's a plot showing, as a function of zenith angle, what the air mass is going to be. So when you're looking right overhead, a zenith angle of 0. Of course, your air mass is 1 by definition, one unit. And then as you go out from there, you can go out to, this is 20 here, it's kind of hard to read, but if you can go out 20 degrees, and you still have, roughly the same amount of air above you. You can go out to 40 degrees here, you get a little bit more, to 60 degrees here, I believe. This is when you've now doubled the amount of air over. So if you go from looking straight overhead to looking 60 degrees over, so 30 degrees above the horizon, you've doubled the amount of air that's between you and your target. And then this happens, right? It really takes off pretty fast after that. So you can go from air mass of 2 to the air mass of 3 about here, and then after that, you're really starting to look through a lot of air. Of course, if you're in the plane parallel approximation, that goes to infinity, but fortunately the Earth is curved, so it just goes off to a pretty high number, around 40 or so. All right, so yeah, so the gist of that is, I'll hit this again, but you typically want to make observations when your air mass is less than 2 if you can, certainly less than 3. Above that, it becomes really impractical to do observations pretty quick, so it's to be avoided. All right, air mass has an effect on your targets, on how bright it is and how many photons you're getting. You guys ever enjoy the sunset? You go out and you look at the sun, right, and you see it going down, it's beautiful, nice romantic moment, right? You ever stare at the sun when it's directly overhead? No, you don't. And you don't because it's much brighter when it's overhead than when it's on the horizon. You can't look at it overhead. It'll hurt your eyes. It'll damage it. Don't do that. But when it's setting, it's okay to look at for short periods of time. Don't stare at it again. And of course, that's telling you that you've lost light. Light, when you're looking through more atmosphere, you're getting fewer photons. And that's what we don't want to do as astronomers, so we want to make sure we're looking above overhead, targets overhead. Also, I should just quickly notice that the color of the object also changes. It goes from, on the horizon, it's usually kind of a reddish color. Overhead, what color is the sun when it's right overhead? White, okay. There's a cultural bias in that. If you ask people in different parts of the world, they might say red or they might say yellow. White is a good answer. I like that one. It's really a complicated thing if you look into it. There's these psychological effects. Depends on what the color next to the sun is that really determines what color it is. All right. It's best illustrated by dresses in, what's that? It looks yellow, exactly, yeah. All right. Okay, so essentially said this, we want to make sure that we're not looking too far over because we lose light and objects we lose light in a wavelength dependent way. So, blue light gets more attenuated than red light. Okay, so there's a relationship that we can write for how badly our observation is going to be affected by air mass. Looks something like this. So there's the magnitude of an object that you're going to observe, right? And that's related to the magnitude that you would observe if there was no atmosphere, plus the effects of air mass. So there's your air mass times some constant. And there's also, you have to consider the color of the object as well, maybe a B minus V color. that's also going to change its apparent brightness in some band. If you're looking in, say, the V band or the G band, these will be different terms. So those K1 and K2 need to be calibrated for your instruments. Okay. Yeah, we already kind of said this as well. So as you get to those higher air masses, very rapidly you start losing photons, and you get to a position where you need to take longer exposure. So if you're trying to collect a certain number of photons, say I need 10,000 photons because I want to get a Poisson noise of 1%. Depending on what that zenith angle is, you're going to have to do a longer and longer and longer exposure, right? Things get even worse, though, because in addition to being attenuated by the atmosphere, you also have to contend with seeing. So we're looking through this atmosphere as making your stars wave around. The closer you get to the horizon, the more they're going to start waving around because there's more atmosphere in there. So you're going to, again, the stars are going to be puffed up into bigger seeing disks, and you're going to need longer exposures. Also, the sky can be brighter because, again, the sky's glowing, and you're looking through it, so there's more of it. You're going to get brighter skies. There's also issues with light pollution when you get lower. I don't know how bad light pollution is for the GROWTH telescope, but for us in Mountain Lagoon Observatory, if we get low enough, we start looking towards San Diego. And San Diego is a pretty big, bright city, so it's not ideal. So light pollution matters. Okay, so you know that you want to look up overhead. That's kind of the short answer. Now that you know that you want to do that, you want to know what you can observe that's going to be up overhead. So you got to pick some targets. This depends on your science, so I can't tell you what to pick, right? You have to figure out what is your goal as a scientist at this point. But once you've done that, you need to make a list of those objects, of course. And a standard list, you're going to have the name of your target, its right ascension, its declination. In some units, it could be degrees are popular these days. They didn't used to be. And you should also specify the epoch for the right ascension and declination. Because right now we're using epoch J2000, right? But you guys are young enough that through most of your careers, you're probably going to be using J2050, right? That's coming up in not so many years from now. So make sure you have that factored in there. You guys know about epochs, right? No? Oh, that's interesting. So here's the deal. Earth is spinning, right? And because it's spinning, and because there's the moon and there's Jupiter that have a torque on it, right? It precesses, right? So that means if you're looking at the North Star at one day, it's not going to be there a few thousand years later or hundreds of years later. It actually moves around like this in the sky. So the North Star is not fixed on the sky, it moves. And because we like our coordinate systems, we define the RA and Dec coordinate system because it's convenient, right? It's convenient to say that that's the right ascension because that's this motion, and that's the declination because it's this motion. Well, if you're precessing, then that's changing, and it's not convenient. So we say, you know what? Every few years, we're just going to redefine the whole coordinate system. That's basically what we do. Every few years, we say, okay, we're going to call that RA Dec 0 now. We used to call that RA Dec 0, but now we're going to call it over here. Right, so that's precession. So when you give somebody coordinates, it means nothing unless you tell them which epoch you're referencing those coordinates to. Where is RA Dec 0 actually on the sky? Okay, so you pick your coordinates and you write them down in a list, and then for what we were doing here, I was talking about how it's important to have hour angles, so you can convert between right ascension and hour angle using a simple equation which I made very complicated. You just take the local sidereal time, you subtract off the RA. I did some transformations here so we account for epochs, actually, the change in the equinox there. I can just keep going here. Sorry to run that cell. Okay, so what you can ultimately do is you can make a plot that looks like this. I like plots that look like this. You don't usually see this, but it's handy for me to kind of visualize what's going on. So here's my targets, and these are actually targets that my students in San Diego State University are observing right now. These are some supernova candidates, type 1a supernova that they're measuring and making light curves for. This is where they fall in the sky. This is hour angle here. This is some number there. I think that's 5 plus 5, 10. Yeah, minus 5, minus 10 in hour angle. And this is your declination. There's declination 0 goes through here. This is, again, in San Diego, so it's a little bit north of the equator. And I'm drawing here these air mass lines. So blue here is an air mass close to 2. No, this is close to 3. This is close to air mass 2. This is close to air mass 1.4. And of course, if you're looking at the North Pole at declination of 90, it's going to be up here. And that's always above our horizon because it's just, moving a little bit. So that's why these lines go out like this. So anything above here and high declinations you can always observe. So what this shows me, though, is I can look at this target here, and I can say, well, in about 2 hours or so, that's going to be on the meridian. All right, so these targets, of course, they stay at fixed declination, so they just move across like this in time. All right, that's why I like this plot. You just look at it, and you can say, this target here, if I want to observe it at air mass, say, above 2, this is how long I have to do it. I have kind of a 7-hour window that I can observe that target. Sorry? Where do you see 4 o'clock? Oh, here? Oh, okay, so I picked this time. This is just whatever I selected. This is in universal time. And if you're in San Diego, 4 o'clock universal time is the night. Right. Yeah, so I mean, if I change this time, then these would shift over an hour or 2 hours or whatever. If I did this for 5 o'clock, this would be about 1 hour over. Again, not exactly 1 hour because there's that 4 minutes a day thing, but pretty close to it for his talk. Yeah. It also shows you this, that some of the targets, the ones at lower declination, because we're in the northern hemisphere, they just kind of skirt above this air mass 2 line here, this orange line. So you have to keep that in mind that if you're observing lower targets, you don't have a very long window to observe them. The higher declination targets, you get much longer time to observe for our observatory. Okay. How's time here? Should it be about done? Anybody keeping track of time? I got you for the rest of the time. This is great. Less than 3 minutes. That's doable. Okay. All right, so you have this concept. Remember, you're not even at the telescope yet. You're just this is planning you do ahead of the time. You say, here's what I can observe. When you actually go to the telescope, you might have a plot like this that'll help you observing as well. But before you get there, you should make some finding charts. So when you're observing, you're going to point the telescope somewhere and you're going to take a picture. Ideally, you tell it to move this Arian deck on the sky, or hour angle deck if you want. Move somewhere in the sky, you take a picture. You should get where you told the telescope to move to, right? It doesn't always happen. So it's good to have a picture. This is what I expect to see. You see on the computer what you actually get, and you can say, well, I got to move this over a little bit, right? So having a finding chart is handy. It's also very important if you're doing spectroscopy, right? Because you may need a very, very accurate pointing. You may need to a fraction of an arc second. You may need to get that to a particular pixel on your detector. And that's just hard to do. It's hard for a giant telescope to move to a fraction of an arc second with accuracy. So what you typically do is you tell it to point over there, and you do a tiny movement to align the target where you want. So a finding chart helps whoever's at the telescope, moving the telescope to know if they're on the field or not. So you should make a finding chart. It should look something like this. You should have a picture of your thing. You should have it nicely labeled. There should be an arrow or something pointing like this is what I want right there. I don't care about that galaxy. I like the supernova here. Make sure you highlight that. Because if you send this, you might send this to somebody else to do the observations for you, and they say, well, it's a cool galaxy. I'm going to observe that. Make sure they know this is what you want. It also helps if you're doing spectroscopy, especially to have these other targets, these other stars nearby, where you know the offset here. So the observer can say, oh, okay, there's a nice bright star there. I can definitely see that. Maybe I can't see this one because it's too faint or it's obscured by the galaxy. But they can put this one in the slit, and then they can do a prescribed offset from here to here to move that star or your target to the pixel it's supposed to be on. All right, so I'm not going to say too much about this, but obviously you're going to have to know how long you're going to keep the shutter open. How long do you need to observe these targets? And that's going to depend on a number of things. It depends on a number of things. Depends on how bright the target is. Depends on how big your telescope is. How well your telescope accepts light and converts that into a signal. So what the seeing is, the air mass, of course, as we've been talking about. You have to factor in all these things. So depending on what instrument you're using, there might be a exposure time calculator provided that will help you do that calculation. If not, what you can do is you can go to one of these websites that someone else has done this for, like these nice ones that NOAO has put out. And you can go to their website and you can say, I have a telescope that's similar to this 0.9 meter here, and I'm looking at a 20th magnitude object. And I want a signal noise of 10 at this air mass and with this seeing, and you can calculate that, and then it'll give you some numbers, and it'll tell you that you have to expose in the B band for 17 seconds, right? This is a fairly bright target. All right, now how the hell do I get back to the other thing? Full screen, go to this tab, view full screen. Okay. All right, so once you have all that set, you know how long you need to observe, you know what you're observing, you have to actually make a plan for the night. This is where we kind of put everything together, and you say, all right, what I like to do is I like to do like a file that looks like this, actually. And so the first thing I do is I figure out, when is the sun going to set? When can I start my nights? When is the twilight in? When does it get dark enough that I can actually take my observations for my science targets? When's the middle of the night? That's my halfway point. I need to know that by then I have to have half my stuff done. So I write that time down. When does the moon rise? Because the moon is annoying, right? It's bright, and anywhere near the moon, you're not going to be able to do any observations if you have a faint target. And then when's the end of the night? When's the twilight start, and when does the sun come up? So I write down those times on this file, and then I start filling in what I want to do. So even before the sun sets, I can take calibration data. I can take a test exposure, I can take my biases, I can take my flat fields. We'll talk about image processing on another day, but you get your calibration data before sunset. After the sun goes down, it's still too bright maybe to get science targets, but again, you can get calibration data, you can focus the telescope, you can get your standard stars observations if you're doing those. And then after twilight begins, you can go through your targets. So I write them down, and I say roughly how long is it going to take to observe. And you have to keep in mind the amount of time that you need to open the shutter, the amount of time you need to read it out, to change filters, to point the telescope. That all needs to be included in here. And write down all those and make sure you have the total sum of those times is between here and here. So you got 5.5 hours to go from here and here. Make sure you have 5.5 hours of observations lined up there. And you might want to refocus the telescope at some point, or do some standard stars with some other calibration data too. So I write a file like this out. And what's good about this is my plan. When I go to the telescope, I know what I'm going to do. And then when you get there and it's cloudy, well, okay, I'm going to change that 20 to 40, and I'm not going to do this one because that's too faint. And you can kind of redo the plan on the fly. So for me, this is very helpful. Yeah, keep in mind things about when is it going to be dark enough for me to do my observations? What calibration data do I need? Make sure you have some priorities on what your targets are. You got to say, this target over here, that's the one I care about. That's the gravitational wave event one. So these other ones, so I'll give you some props here, right? These other ones maybe I don't care as much about. So you got to make sure you get that one, and maybe you'll change your strategy a little bit. Maybe you'll say, I'm going to catch this one the second it rises above an air mass, a reasonable air mass, because I want to make sure I can hit it. Or maybe I'm going to follow it to air mass 6, which was actually done for this gravitational wave event. People say, I'm just going to do whatever I can because it's more important than anything else. There are some nice tools out there that can help you plan your night and work on it during the night to come up with what you're going to do next. I like this little package called JSkyCalc. I've been using that for a long time. But of course, if you're a modern astronomer and you got your Jupyter notebooks and your Python set up, there's a package called Astroplan, which has basically everything that you need to do, has everything that you need to calculate sunrise times, moon phases, altitudes, moon separations. You can make finding charts, and you even have some scheduling built into there. So you can actually, on the fly, go through and change your schedule and figure out what you're going to observe next. No one's sharing this one, so I'm going to say that's time. but hopefully that gives you some idea of how to plan for an observation run. Okay.
So we can take one or two quick questions, and then we can start the actual hands-on module component. Any questions? Excellent. Before people realize that they could have asked one, I'm going to She did.
What is meant by unextincted brightness?
Unextincted is a terrible word that just means not attenuated by the atmosphere. So unextincted means, when you look through the atmosphere, there is a loss of light due to the atmosphere. And if you correct for that, then that's unextincted. Yeah, so it depends on what you're doing. So I try to make this a little bit general. But if you're doing imaging, then you need to take an exposure called a bias frame that says, if I have no photons reaching my detector because I kept the shutter closed, how many ADU, how many counts do I get on my detector? Because it's not going to be zero. It's going to be 400 or 1,000 or something, even if you get no photons. So you need to calibrate that. And then you also need to say, let's take an exposure where every pixel gets the same number of photons. So you get 10,000 photons in every single pixel. You're not going to get the same number. You're going to get a different number for every one of those pixels. So that's a flat field that helps you correct for those pixel variations. So you need to do that for imaging or spectroscopy. With spectroscopy, you also need to calibrate your wavelength scale. You can use the skylines, but people commonly observe a lamp that has known lines, so you know where your wavelength scale is. And you also need to observe standard observations. So you observe a star where you know what its brightness is. Someone's already calibrated it for you. And so you say, well, I got 10,000 counts from that star, and I know that's 15th magnitude. So this other one I got 5,000 counts for, and I can figure out what the magnitude is.
Some of these details are also going to be covered in modules that will come up during the
Get this out of the way.
So, yeah.
I'll just leave this here. I don't know if that's...
Robert, one more question.
One more question. It may, a little bit, but to a very good approximation, it's just what the zenith angle is. For things that we care about. So again, I advise you against observing above an air mass of 3. So if you're above an air mass of 3, so a number smaller than air mass 3, it's very confusing. It doesn't vary so much depending on season, but a little bit, yeah. But I wouldn't worry about that too much. That's what the calibration data is for. Local sidereal time. So yes. Your right ascension, the RA, that is fixed on the celestial sphere. So if you have a target that's off an infinity, you can think of like distant quasars. They're basically you're accounting for the fact that you're on the Earth when you look at hour angle. So your hour angle is I'm on the Earth and I'm spinning around, and you're a star that's really far away. So I can think of it. There's some kind of coordinate system set up by the people sitting in chairs here, right? And if I'm spinning around, whoever's in front of me depends on the time and how fast I'm spinning. So hour angle is saying, well, in 30 seconds I'm going to be pointing over here at that person, right? But you're not moving, right? This is me spinning around.
Okay, let's thank Professor Quimby again.
Right.
And now we will switch to the observing plan hands-on module. I hope you have the module opened up. Your instructor for the module is Dr. Shubham Srivastav. He's done his PhD at the Indian Institute of Astrophysics in Bangalore, and then he joined IIT Bombay, where he is now actually the project scientist for the GROWTH telescope. So he's the chief scientist for the project, which has created the winter school that you're attending here right now. All these pictures that you see around here have been taken by that telescope. So let's welcome Shubham and get started with the module.
Okay, hi, good afternoon all of you. I am Shubham. So so this is a module that we'll walk over the concepts that Robert just introduced us to. We'll talk about how to plan your observations, deciding your objects, what you want to observe, how to see if it's observable or not. Not all sources can be observed at all times, at all places. So you have to plan accordingly. You have to look at air mass considerations. Ideally, we don't want to observe anything which is above an air mass of 2, which is angle of 30, elevation of 30, right? But sometimes we have to, if the source is important enough. and then you also want to take into account the moon position. The moon, if it's too close, you want to avoid those sources. So let's start with, everybody has their module opened up, ready to go. So let's start with loading. So yeah, so let's start with loading the basic modules. We'll be needing NumPy, and that's it really. From AstroPy, we need sky coordinates and Earth location, and we will be using Astroplan that Robert spoke about. So the idea of this module is to introduce you to the various things that you can do with Astroplan. I am new to Astroplan myself, so I won't be going into too much detail about specific functionalities. But at the end of it, hopefully you will have an idea of all the things that you can do with this very flexible tool, and hopefully when in the future you're planning your own observations, you can use the ideas that you've learned here. Okay, so date and time, this is the universal ISO format, the YYMMDD format. So as you can see, I did not specify, I only specified a date here, and you can see that it defaults to a UTC of 0. So that's the convention. And so now let's see what is the current time. What is the current UT? Well, the time right now is around 9 UTC, which is, so we are in a time zone which is 5.5 hours ahead. You can also print out the JD, which is the Julian day, and the modified Julian day, and also the decimal year, for example. This is just some of the things that you can do. You can play around with this time function. So now let's see simple exercise. What time will it be after 1 hour 45 minutes from now in UTC? Right, so you can just fill in the blanks yourself. Just try doing this. Should I pause for everyone? Yeah, sure. Okay, so well, what do we have to do here? We just add 1 hour 45 minutes to now. So we just add it here. But we just have to be careful about the units. So let's do 1 and sorry. Yeah. Oh, I'm sorry. It's min? Yep. Yeah, thanks. Okay. So the right. Yeah, sorry about that. So in order to keep accurate time, there's a standard called the IERS, which is basically the International Earth Rotation and Reference System Service. So they they take into account the changing period of the Earth's rotation. The period is continuously changing, right? The Earth's rotation period is changing due to tidal forces, so that has to be taken into account to keep accurate time. And this bulletin does it for us. So let's download the latest bulletin and update it. Okay. So now Astroplan has a number of observatories around the world which it already has the data for. Now, as we know, we talked about, Robert told us about RA and DEC, which are, well, universal, it's a universal system. The RA and DEC do not change, but depending on where you're observing from, the local coordinates of a astronomical source are variable, right? So you want to know where you're observing from in order to plan your observations. So this is a list of observatories which are already available in Astroplan. Okay, so this is a list of observatories that we have, and well, it's a big list, but where we are observing from is the Indian Astronomical Observatory, which is in Ladakh in India, which is not really in the database. It should be there, but it's not there. So let us define our observatory coordinates ourselves. So the Indian Astronomical Observatory is at a longitude of around 79 degrees east and around 33 degrees north, right? So we define the latitude and the longitude. It's a high altitude observatory at 4,500 meters above sea level. So the Earth location, we can use the Earth location to define this location of Hanley, and we create an object called IO Hanley, which is basically an observer object, and that contains all the information about the Earth location and the time zones. You can give a name, a description. You can also give temperature and air pressure and all other parameters. Okay. So now let's see when is sunset. As we all saw, we only start observing after sunset, right? So so IO Hanley is our object which contains our observatory coordinates. So IO Hanley dot sunset underscore time, which is what we can use to find out the time, the sunset. So you can see that sunset is around 11:30 UTC, which is around 5 PM local time. So it's a pretty early sunset in winter at Hanley. And we can also look at the astronomical twilights. So the astronomical twilights is when ideally you should start your observing run. That is when the sun is at minus 18 degrees from the horizon, right? But you also have the civil and the nautical twilights, where the sun is at minus 6 and minus 12. So in practice, you could start observing before the astronomical twilight, but that is when the sky goes pretty dark. So that is ideally when you should start. The middle of the night, which Robert talked about, is IO Hanley dot midnight, which gives us that. So the midnight is around 1834 UTC, which is around 11 PM. Almost 12 PM, right? Around midnight. And the morning twilight is at 0 UTC, which is around 5:30 local time. So this gives us an idea about when we can start our observations and when we have to stop and then plan accordingly. So now a small exercise is to find the effective length of time which is available for you tonight to do the observations. So what you want to do is basically just calculate the time difference between when you want to start, which is evening twilight, and when you want to stop, which is morning twilight. So I'll pause here for a couple of minutes. You can fill in the exercise. So anybody has an answer? 0.457 days. So convert it to hours. That will be easier. Yep, almost 11 hours. Yep. So that's a pretty good so you get a lot of time to observe in the winter. So it's 11 hours from twilight to twilight. But in practice, you can actually do almost 12 hours. You can start a little before astronomical twilight and end a little later, little after morning twilight. Right. Anyone else got the answer? Yes, everybody got it? So this will give you the answer in the ISO format, right? Which is why Prajwal over there told us 0.45 days. So we'll just convert it to hours. Okay. Yeah, so around 11 hours of observations. It's pretty good. So now we come to the local sidereal. Yeah.
What if we wanted hours, minutes, seconds?
What
What is the
is the?
command for that?
Okay. I guess you could do a u dot HMS. You can try that. Is that going to work? No? Or you could just convert the decimal R to minutes and seconds, right? Okay. So everybody with me so far? Okay, so shall we proceed? So now let's look at the local sidereal time. Now, as we talked about the R angle, and it is basically the difference between the local sidereal time and the right ascension of the object. And so now let's find out what the LST is at the Indian Astronomical Observatory. So, yeah, we have LST now, well, it's around 18.8 R angle, and what about midnight? Well, at midnight is going to be around 4.7 hours. So we need to plan our observations accordingly and choose our targets which are visible at different parts of the night. So now let's come to choosing the targets for observations. Here we can, well, there are different ways to define your sources, the targets that you want to observe. You can either define the coordinates on your own using the sky coord. So in here I have defined a coordinate of M32 using the sky coord, and then you can create an object using the fixed target class, and in that I have given here the coordinates as well as the name, right? So we have created a fixed target for M32 here, and you can output the array. You can so let's look at what the deck is. Okay, so around 40.8. So is this target going to be available tonight from the Indian Astronomical Observatory? To see that, Astroplan has a useful function called target is up, and that returns a Boolean value. So it's either true or false. So is the target, well, is it above the horizon or below it? So let's see, is the M32 up at evening twilight at IAO tonight? Well, it is, right? Huh? Any doubt? Right. So, well, M32 is up. Well, doesn't mean we can necessarily observe it at evening twilight. We also need to know how high it is up, but at least it's available in the horizon. Now, as we saw, the RA and deck are the RA and deck are universal coordinates, so they do not change with time. Well, they do, but what we're really interested are in the local elevation and the azimuth, or the altitude or the azimuth of the source. And so the alt-as function can convert the array deck to the local coordinates, the local altitude and azimuth. Of course, these are functions of time. So you can use this alt-as function, and the arguments will be a time, which is in this case I have given a midnight, and a target. So you give a time and a target name, and you get the altitude and the azimuth. So here the alt-as of M32 at midnight is 42 degrees elevation and an azimuth of around 300 degrees. We can also check the time of rise using the rise target underscore rise time. So for example, when is M32 going to rise today at the Indian Astronomical Observatory? We use the target rise time function. And here I have given a horizon equals 0, but you can also change the angle over here to know that it's going to rise at this angle at this particular time. Right, so our M32 is going to rise at around 6 UTC. So it has already risen, and that's why it's already available. Another way to define our objects is to define them by name. So Astroplan already has a catalog of names, and a lot of targets have already been saved. All the Messier objects, for example, the NGCs, a lot of stars, and so this is an easier way to do it. You define a target using the fixed target from name, right? So for here I am creating a fixed target object from name for M33, and these are the coordinates. The RA is around 23 degrees and the deck is around 30 degrees, plus 30 degrees. Now we already saw that the moon can be kind of a nuisance for observations, and we want to stay away from it, especially if it's full moon or around. You want to stay away from the moon at least around, say, 20 degrees. So now let's see how to find the moon positions and the sun positions. These are of course moving targets, in the sense that their RA index is not fixed, but for the purpose of checking, we can treat them as fixed targets by defining them by the fixed target class, and we can plan our observations accordingly. We can also check the illumination levels of the moon. Okay. So get body is the way to do that. So feel free to change this Jupiter to different planets to see where all the planets are right now. So get body Jupiter now is telling me the coordinates of Jupiter right now, right? And this is the last value. It's the distance in astronomical units. So the distance is around 6.3 as AU right now, and the elevation is minus 20, which means that it is below the horizon. What about the moon tonight? So let's get the moon at midnight. So at midnight the moon is at minus 6, which is good. So when the night is darkest, the moon is below the horizon, which means that we don't have to worry about contamination from the moon. And what about the illumination levels? It's only around 0.13. So the moon is just 10% bright tonight, right? So good observing conditions. So now, well, Robert has already told us all we need to know about air mass. Ideally, we don't like to go below an elevation of 30, which is an air mass of 2. But for the GROWTH India telescope, we can go down to around 15 degrees elevation, which corresponds to an air mass of much higher than 2. It's almost an air mass of 4, in fact, right? So it's 3.9 at 15 degrees. As we saw, the air mass blows very rapidly after an elevation of below an elevation of around 30. So in general, we try to avoid air mass of above 2. So now let us find the air mass of M33 or whatever your favorite source is. So our target right now is M33. So let us find, well, first of all, is the target up? So that is true. So great. But at midnight, M33 is available. Now let us convert the array deck of M33 to the local ALTAS system, and well, we get an altitude of 50 degrees. Right, so that's a good enough altitude to observe the object. The air mass is not very high. What is the air mass? Well, you can calculate the air mass using the sec-z function. So the air mass at midnight for M33 is around 1.3. So well, it's lower than 2, so we can go ahead and observe. Okay. So now, any doubts so far? Any questions? Yeah. 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 Well, these are moving targets. The planets, they're moving with respect to the background of the fixed stars. But for the time being, you could consider, to find their positions, you could consider them as pseudo-fixed targets. Yeah. Any questions so far? So yeah, so now let's do some plots to actually look at what we are talking about. Right, so we import matplotlib and a plotting function in Astroplan itself called plotsky to get us neat sky plots. So this is a sky plot of our target, which is M33, which I defined. You can choose your own target at Indian Astronomical Observatory at midnight. So this plot tells us the position of our target at the time that we specified. So it is around, it's slightly below 60 degrees elevation, and the azimuth is around 270 degrees. Now what if we want to see how this position changes as a function of time, right? We want to get a sky plot as a function of time. So let's see how the target moves over the course of the night. So here let us define a time grid. So that is roughly, the start time would be the time that we are starting our observations, which is, yeah.
How many of you are getting a problem with unknown property frac?
Yeah, I'm fixing it.
Okay,
So I'm spinning a pull request to fix it.
So that is something which is happening in some of the systems and working in others. It should work in all systems, but as Leo Singer just said, this is a problem with the backend software itself, which he is requesting a fix to the authors who are maintaining that. So for now, if you got that error, just skip over it and we'll go to the next part.
Okay, so we define a time grid. So you want to start at approximately astronomical twilight in the evening. So that's our T start, a T end at morning twilight, and then we define a grid of times using the lin space in NumPy. So okay, so we have a grid of time now, and we can find the elevations at different times and then make a plot, right? So okay, so this is also not going to work then, the other plot. Yeah, okay.
Okay, let me, since there's a lot of discussion starting. Basically, there's a property which they have used, which was supported in older version of matplotlib, but most of you, if you have done a clean install, then you have matplotlib 3, which does not support that option anymore. So that will get fixed. Right now, there are 3 possible workarounds. One is you find a system where this works. 2 is that you actually downgrade your matplotlib to version 2 point something. And 3 is we move on to the next cell. So let's go with option 3.
Okay, but at least you can take a look at what the plot looks like. Right, so this is how M33 is going to move across the sky over the night. You see that it rises around here and then moves westward and then it sets. So now let's come to the air mass. So let's plot up the air mass. We can do that using the plot underscore air mass. Any doubt? Okay. So if you do not give this limit, the Astroplan itself has a default air mass of around 3. So it's not going to show you where the object is below an air mass of 3. So it's basically telling you don't go below 20 degrees. But for the Growth India, you can actually go to 15 degrees. So that's why I changed the air mass to around 4. And you can see that, as we saw before, it's a very sharp, very steep fall after an air mass of around 2. So this is what the air mass of M33 is looking like for tonight at the Indian Astronomical Observatory. So now we obviously want to observe it in this window, right, where the air mass is the highest. So we don't want to go beyond this where the air mass falls to around 2. So we plan our observations accordingly so that we finish this target before 20 UTC. So the air mass is, well, less than 2 for the better part of the night. As a typo there, I said above 2, should be below 2, making M33 a good target from IAO for tonight. So now we can also plot finding charts. So let's see what a target actually looks like. It's useful when you have the image but you want to identify your source. You want to find a chart. So that you can do using the sky view function. So this is a finding chart of our target, which is M33. And for the Growth India, the field of view is around 45 arc minutes. So it's pretty wide field, around 0.7 square degrees. But the field of view radius is what you can use to define your field of view and get your finder chart accordingly, depending on the telescope that you're using. Huh?
It's the radius.
FOV radius. Oh.
45 by 2.
Okay, yeah. Okay. Right. But I don't know if he's connected. Yep. So this is what a Growth India image would look like. So now typically, obviously, you don't have one target to deal with in a night. You will be having a list of targets that you want to observe. So here we define a list of targets called target names, and we just store the target names in a variable called targets, and we store them as fixed target objects. And all of these are targets whose names are already contained in our database, so we don't actually have to give their coordinates, but we can do that. So now let's see which of our targets is up. You can do that again using the target is up functionality, and so now we get a array of Boolean values, right, for all our targets. So 2 of them are down right now, 3 of them are up. Well, you will have noticed that one of them is the pole star. So that is always going to be up, right? It's a circumpolar object. Which of these targets is up now, and then we can also see which of them is up at evening, at midnight. During the course of the night, we can plot their positions, which we have already seen how to do that. So small exercise here, find out the times at which the targets rise to an elevation of 10 degrees. So basically your output should be an array of times where it tells you which of the objects rise above 10 degrees at what point of time. So you can try this exercise, but I want to go through the other things that we can do. So now let us try and see what the elevation looks like, right? We can also plot the elevation using the alt-as function. We can get the alt-as at any given point. We can find it, the alt-as of target 0, which is our first target, which is Vega, right? So the Vega, the position of Vega right now is around 83 degrees elevation, so it's pretty high up right now. So now let's see how it varies over the night. So again, you can define a grid of time starting around the evening twilight, ending around the morning twilight. And then for each of those times you have an elevation, and so now we can plot what our elevation, how the elevation varies as a function of time. So this is what, well, this is how it's moving over the night. So this is just the elevation, right? So you can see that the altitude is around 40 degrees at the beginning of the night, and then it, well, it sets and then goes below the horizon. So now a simple exercise would be to get this plot for all your targets. So just loop over your targets using a simple for loop, and you can make this plot for each of your 5 targets that we have defined. So you can try these exercises. I'll just go through very quickly over an important aspect of Astroplan, which is incorporating constraints in the planning of your observations. Right. So as we saw that not every source should be observed at all times from all locations. The obvious constraints are obviously at night constraint, which is, well, you only observe your target if it's night. So that's the first thing you check for. Then you look for the air mass, if it's at a good air mass or not. The altitude constraints. So for the growth India, you don't want to go below 15 degrees. The moon separation, depending on how bright your source is, but you don't want to go too close to the moon, especially close to full moon. And so we can incorporate these constraints, and I have defined here an altitude constraint. There's an upper limit of around 84 for the growth India, because for an all-task telescope, tracking at high altitudes becomes a problem. So you also try and avoid very high altitudes for an all-task mount. So yeah, so we can define, here I have defined the at night constraint as a civil twilight, which as opposed to the astronomical twilight. So that gives roughly half an hour before the astronomical twilight. So once we have defined these constraints, now what we can do is get a table which tells us a lot of the things that we need to know. Is it ever observable during the night? So that we can get from the ever observable function. So that tells us that is the object going to be observable at any point in the night, right? So here we give the constraints and the targets and the time range during which we yeah, okay. So then there's an always observable task, which tells you if again it returns a Boolean value telling you if the object is always observable in the sky. So for the pole star, for example, that's going to be true. You can also find out the best months for observation using the months observable, and when you feed in the constraints, I have not I have not taken an output, but you can do that. Just print obs months, and then you can see the best months for observations for all these objects. So these arrays are the outputs of the is observable and always observable functions. So we can see that 4 out of 5 of them are observable tonight from the IAO, and only one of them is always observable tonight, and obviously that's the pole star. And then you also get a list of months which are best suited for observing these particular targets. Now what we can do is we can also put this in the form of a table, right? So we can actually define an observatory table using the astropy table function. So this gives us, well, we have defined 3 columns here, the target names, ever observable and always observable. Right, so that returns a Boolean column about the observability of our sources. But an easier way to do this is to use, so this observability table is already inbuilt in Astroplan. So all you have to do is feed in your constraints and the observatory location and the target lists and a time range, and you can actually directly print out this table using the observability table. And another neat feature of this is that it gives you the last column is the fraction of time observable. So what fraction of the night is the source actually going to be observable from your observatory? So this is very useful in planning your observations. So if you have a high priority source which is observable for a small amount of time, you want to make sure that you want to observe it in that window. Okay, so final exercise that you can work on is, well, you can create a list of your favorite targets, create a text file with name, array and dec, 3 columns, and then write a code to read this file, so that now you've, and once you read the file, you can get this observability table for all the targets in your list. And you can also plot, you can try different constraints, you can actually see how the fraction of observing time changes as you relax your moon separation constraints, for example. And you can also plot their air mass, plot their sky positions as a function of time, their elevations. Yeah, I think that's it.
So we've covered a lot of ground in this module, right? There's a lot of new functions that you heard about the first time. How many of you are amateur astronomers? How many of you have gone stargazing ever? Okay, can you tell me what other name you know M33 by? Do you see triangulum around here somewhere? Okay, so you can now actually compare that printout of triangulum with what Astroplan told you it should look like, see if the field of view makes sense and so on. Okay, but there are a lot of exercises that we went through very quickly in the end, and the idea was not to complete all of them interactively. A lot of them are meant for you to try out by yourself. Okay, and tonight we are actually going to have an observing session. Now we discussed in the beginning of this module as to whether the night will be longer in Mumbai or in Hanle. Hanle being further north, and we are in winter right now, so Hanle actually has sunset earlier, which means that we can actually start our observing session around 5:30 itself. Okay, so there will be a live observing session from here with the Growth India telescope at 5:30. We want you to work on these exercises, not just on M33. Pick your favorite object. Okay, the idea behind this evening session is really to get to learn what we can do with a telescope, what we cannot do. Would you come up with, trying to observe the sun at midnight? Would that really be a good idea? How do you choose targets? Just because you really want to observe Orion Nebula does not mean you can see it at 5:30 today. Maybe you can, maybe you cannot. So pick your favorite targets, work through this exercise, go through it again. Of course, as was evidenced by lunch break, none of you really like lunch or tea anyway. So you are going to sit here and continue is my guess. But whenever you get a chance, try to go through these. There's a lot of material here. Work through the steps again. Tutors again are available to help you. And then for the evening session, it's not a formal structured session like this one. Okay, so that is where we are really going to ask you what do you want to observe, and if you don't answer, then we are just going to sit here and stare at you for a long time. Okay, so really come up with your list of favorite objects. We'll try to get as many images as possible, and we'll pick few of those images and use them in further modules tomorrow and day after. Okay, so we'll stop here with that and head out for a tea break, and we'll resume again in half an hour. So let's thank Shubham and Robert Quimby again.